Visual context, particularly facial expressions, play a key role in understanding the intention of a message. The speaker on the left is trying to convey a positive meaning, while the speaker on the right is clearly doing the opposite. But visually impaired individuals lack this context. So imagine an application that is able to interpret the facial expressions of a subject in real time. Imagine something like this.
Happiness, sadness, surprise,
My name is Pablo,
neutral.
and I made this real-time emotion detection application for the Summer of High-Performance Computing, under praise and 94 innovations. In order to make a machine understand facial expressions, we need a way to encode an image, an array of pixels, in a way that its emotion is easily classifiable. The face images I'm going to be using are 224 by 224 pixels, making them 50,176 dimensional objects. So instead of pixels, I'm going to be using a lower dimensional encoding, action units. Any facial expression can be reduced to a set of action units which encode combinations of muscle movements. The most common facial expressions, like happiness or sadness, can be encoded using only a handful of action units, 17 to be precise. In order to make this encoding from the pixels of a face, I used a deep neural network. A neural network is a computer system inspired in how neurons work that is able to find underlying patterns in data. These models are able to learn these patterns by seeing thousands and even millions of examples from which they learn from. The data I needed to train the neural network came from 4 existing datasets that consisted of footage of spontaneous emotions with the active action units annotated frame by frame. I went through an array of different processes to improve the quality of this combined dataset. This involved balancing the frequencies of the classes, cleaning noisy labels, removing contiguous frames, and augmenting the data by applying random rotations, shares, zooms, and brightness shifts to each image before feeding it to the network. Building and training a neural network is a very time and resource-consuming process. For that reason, I reused the convolutional layers from an existing network called VGG-Face. This common practice of reusing parts of existing networks that were devised to solve problems in a similar domain is called transfer learning. So let me explain what the convolutional layers that I took from VGG-Face do. A convolution could be understood as a filter that's applied to an image. So convolutional layers are just a bunch of these filters acting both in parallel and in sequence. Superficial layers encode low-level concepts like edges or corners, but deeper ones become less interpretable as they encode meaning related to the class of the image instead. So the output of the last convolutional layer could be thought as the high-level features that define a face. Now all I need is a classifier on top of that is able to map these features to the active action units. For that, I used a bunch of dense and dropout layers. Dense layers could be thought of fully connected layers of neurons that fire an output only if their inputs are high enough, same way neurons behave in our brain. Dropout layers, as their name implies, drop a random fraction of the units in the training process to stop the network from memorizing individual images and instead learn the underlying pattern. During the training of the neural network, I explored a number of hyperparameters and settings, like the learning rate, the batch size, the number and size of dense and dropout layers, and different pre-processings of the data. Now that we got a neural network to infer the active action units in a face, all we have left is to find a way to infer the emotions from them. Let's start by visualizing how different emotions look in this hyperdimensional space, where each dimension corresponds to an action unit. I generated these data points by having my model predict the action units from faces depicting one of the basic emotions. The value of each dimension is the probability of the corresponding action unit to be present on the face. There are clearly separate clusters corresponding to each emotion, which proves the robustness of encoding emotions using a few action units. So predicting the emotion that corresponds to a newly seen vector is just a matter of looking at its neighbors. See this new prediction? By finding the most common class in its neighborhood, we get the most probable emotion. I deployed this pipeline to an application that is able to infer the emotions synchronously every fifth of a second and average them over time to foster stability. Besides, the fact that these emotions are predicted using action units makes this application very easy to extend, as all you need to do for the app to recognize further emotions is to add a few data points to the neighborhood corresponding to the action units active in them.
Happiness, fear, anger, disgust, happiness.
Okay, so
Neutral.
thanks for watching, and goodbye.